Light is made up of particles called photons. Photons act as both a wave and a particle. These photons have energy related to its momentum, which is a function of its wavelength and is related to the speed of light. The smaller the wavelength, the more energy the photon has. Photonic crystals allow for control over the propagation of this light. These crystals act similar to electrically conductive materials, but at a much smaller scale. The crystal in electrically conductive materials is a periodic arrangement of atoms and molecules. When this pattern is repeated, it forms a lattice. The constituents and geometry of the lattice determine the conduction or propagation in the case of the photon through the crystal. In a photonic crystal, the medium that acts as the lattice structure is a dielectric material. Changes in the index of refraction of the medium change the wavelength of the photon and work to impede the propagation. This interference causes the photonic band gap, which acts as a crystal structure. The photonic crystals can be found in nature. Examples of this include the butterfly wing and the opal mineral.
Photonic crystals have diverse applications. Some of these applications include thermal camouflage for military use and optical coherence tomography for medical use.
Photovoltaic, or PV, technology is considered to be a promising technique for solar energy utilization. Among all the semiconductor solar cells, silicon-based solar cells have dominated most of the PV market due to the abundance and the well-developed technology of silicon. The efficiency of thin-film Si solar cells critically depends on optical absorption in the Si layer, since single crystalline amorphous and microcrystalline silicon have low absorption coefficients in the red and near-infrared wavelength ranges. In recent years, thin-film Si solar cells still show inferior performances compared to their bulk crystalline Si-based counterpart. Therefore, an effective light trapping design is used to achieve high-efficiency modules. Traditional light trapping schemes, such as textured transparent conductive oxides, or TCOs, and metal reflectors, lack the ability to precisely control and optimize the energy absorption. Recently, 1, 2, and 3-dimensional photonic crystals have also been proposed to enhance the light trapping in PV cells. Photons from a light source, usually the sun, strike the semiconductor material, such as silicon, and ionize it, which results in electrons breaking free of their bonds. The electrons are all forced to flow in one direction, thus creating an electric current. Photon management strategies, including light trapping, have been successful in improving efficiency and cost reduction in practical solar cells. This is where photonic crystal technology comes into play and reveals the advantages of its utility.
Normal solar cells are formed with thin-film silicon cells with silicon oxide-based Bragg reflectors, as well as wave propagations. These simulation cells have periodic boundary conditions in the lateral directions, and under normal incident light rays, they are totally reflected back into the atmosphere with less absorption, making solar cells very ineffective. However, when the solar cells consist of 2D or 3D photonic crystals in the Bragg-based reflectors, which are made of triangular lattices of cylindrical air holes embedded in the silicon, such an optimized 2D photonic crystal structure can provide a complete band gap for the light rays. Furthermore, the light incident on the 2D photonic crystal is not totally reflected, but also diffracted because of the sequence introduced in the lateral direction. Furthermore, increasing the light path length and provides better light trapping performance. These photonic crystals are used in increasing the solar cell effective and efficiency.